Hey, good morning, everyone. Let's begin. So today we'll begin with chapter 1, and chapter 1 is a little bit of brief recap of circuit analysis, as well as what you can expect in 306, and then a little bit of what you can a little bit of talk about circuit analysis techniques. Okay, so this is something that you've already done in 113, but it was a long time ago. One thing I would like to point out, you will keep using those circuit analysis techniques all throughout your education. Actually, pretty much for your entire professional career. Okay, and so I always like to do chapter 1 and give some time for practice problems for circuit analysis. So let's. Okay, there's the class notebook. All right. No. There we go. Introduction to electronics. Okay, so primary differences. So far, you have learned about electric circuit analysis, right? So what's the difference between electric and electronic? Okay, electric circuits mostly comprise of linear elements. The three most important ones that you've dealt with are analyzed are resistors, inductors, and capacitors, right? They're all linear. Linear in the sense that the voltage and current have a linear relationship. If the voltage increases, the current increases in a linear amount. If the current increases, voltage increases in a linear amount. So they have a linear relationship. Okay. For electronic devices, we will learn about nonlinear elements. Okay, nonlinear elements. And nonlinear elements are the semiconductor devices, starting with the 2-terminal diodes and 3-terminal transistors. In transistors, we will look at BJTs and FETs. Okay. So these are non-linear elements because the voltage and current do not have a linear relationship with each other. By the way, if you can't read my chicken scratch, then please let me know. And I will, sometimes I'm in a rush, and so I just tend to scribble. Okay, so that's the key difference between linear and non-linear elements. Okay. So in this class, electronics, we will look at electronic devices, which are diodes, FETs, BJTs. For electric circuits, the analysis is straightforward. We use analytical methods. Analytical methods, simply stated, means you have certain equations, you plug in the values of those of the variables in those equations, and you can expect a direct answer. Okay, so that's an analytical method. So, for instance, for circuit analysis, you learned about Ohm's law, learned about KCL, KVL, the power equation. Those are the only equations that you would actually need for all circuit analysis techniques. By the way, Ohm's law, KCL, KVL. From these three, you derive node voltage analysis, which is nodal analysis, then mesh current analysis, voltage division, current division. All of those are based only on these three equations. Okay, Ohm's law is V equals IR, KCL and KVL basically is based on the law of conservation of energy. So these three equations are the only three equations that you need to know to analyze any circuit. And then all the other circuit analysis techniques, which are derived from these three equations or these three principles, is basically what you will use in this class and going forward. That's it. All electronic devices can be described using different models, and that's where this comes in. So for electronic devices or for electronic components, we use numerical methods. So the difference between analytical and numerical is that analytical is exact, numerical is approximate. Okay, numerical methods Oftentimes, we will make use of assumptions. We will assume certain conditions for our devices, for our circuit. We will assume some values. Some of the values will be given to us, and we might assume some values based on certain logic and certain circuit rules. And then once we have those, we calculate, we go through the steps, we find out the answers. And once we have an answer, we verify with our assumption at the beginning. Meaning, if we assume that a voltage has to be within a certain range, we make that assumption, go through our analysis using that method, find out the values. At the end, we compare the value with the assumption that we made at the top. If it matches up, great. If not, we change our assumptions and we redo the analysis. We keep doing it until the end result matches up with our original assumptions. And that's basically numerical methods in a nutshell. The reason for that is no single model can describe an electronic device, or no single model would be appropriate to describe one single electronic device under all conditions. Even the fundamental principle, Ohm's law, like voltage is equal to the product of the current and resistance. So V equals IR. Even that is not valid outside of certain ranges. Extreme temperatures, extreme pressures, outer space, perhaps, different different environmental conditions, Ohm's law will no longer be valid. Okay. But for all intents and purposes, we say, okay, Ohm's law is standard, it's valid, because what we are always talking about is like room temperature conditions. And room temperature conditions would be between 20 and 40 degrees C. Technically, room temperature would be defined as like 27 degrees C. Depending on the author, depending on the book, everybody likes to use their own values. Okay. All right, let's take a pause, think over all of that. Let me know if you have any questions. Any questions? Okay. Yeah, it should be. Give me hold on. Okay. One more point about these models. Can make an analogy about describing yourself. So if you have ever been to an interview, maybe for an internship, maybe for a full-time position, sometimes maybe your interviewers, maybe it's HR, maybe it's a technical manager, might ask you, describe yourself in 10 words. And it's a very valid question. It's something you should think about if you have never ever done it. Okay, because many other variations of this question could be, tell me about yourself. Okay, so that is the moment in an interview that you speak about yourself that is not already conveyed in the resume. Okay, your resume would be about your quantitative accomplishments. Your qualitative, meaning subjective, what kind of a person you are. That's something that will not show up on your resume. So tell me about yourself. It's a very valid question that you would encounter in interviews. So if I ask you, describe yourself in one sentence or describe yourself in 10 words, you'd be able to do it. There are many words you could choose, just adjectives, whatever comes to your mind, right? Then if I say, describe yourself in 5 words, it gets a little harder, but you would still be able to do it. If I ask you, describe yourself in 1 word, what would that word be? You don't have to disclose anything, but that's something to think about. And all of those can be true. Your 1-word description is true. 2-word description would also be true. 5-word description will also be true. And a 10-word description about yourself will also be true. The point I'm trying to make is that we will use several models for these devices. And each of those models will be valid to describe those devices under certain conditions. Okay. So oftentimes we might choose one model for quick and easy analysis. And other times we might want a very detailed model because we need to consider the effects of temperature, pressure, and environmental conditions. So depending on the application, as an engineer, you would decide which model you would like to use. There's no right or wrong. Okay. Even in the answers, of course, there's a method and we need to have like accurate answers. But in general, as an engineer, if you're working, there are no right or wrong answers. It would be up to you to verify whether it's correct or not. So you would use 2 or 3 or maybe even 4 different approaches and see which answer matches up best. Okay, make sense? Okay. All right, so the electronics courses that you will take, 306. 306 is where you learn about some semiconductor fundamentals. You will develop models for your devices, right? And you will analyze these models for the use case scenarios. And then next quarter, you will take 307. The quarter after that, you would take 308. It's one academic year, exactly the same as 113, 211, and 212. And no matter where you go in this world, if you are studying electrical engineering, you would take circuit analysis for one academic year, and you would take electronics or electronic analysis for another academic year. Okay, it's the same worldwide. So 306 is fundamentals of semiconductor devices and circuit analysis of those devices. 307 is basically digital electronic circuits, where you use the exact same components and you create digital circuits. And in 308, the exact same devices, and you create analog circuits. Okay. And then you put it all together in 409, which would be about the first class that you would take in your 4th year, which is electronic design, which is then referred to as mixed signal electronics, which nowadays many of the electronic devices that we use nowadays, consumer electronic devices, are mixed signal devices. Case in point, for example, would be like a smartwatch or a smart device, which has multiple analog sensors plus digital circuitry to process those. Okay, and so that's something that you would do in 409. Anyway, so just as 113 is fundamental and important for circuit analysis, 306 is fundamental and important for the rest of these classes. All right, so the evolution of electronic devices began with the invention of the vacuum tubes. Now, vacuum tubes have been around for a long time, okay? Compared to the modern devices, they were bulky, okay? But when they first came out, I would say a typical vacuum tube would be about the size of your finger, probably about this big, and the width of our thumbs, okay? And the earliest vacuum tubes had 2 electrodes in them, okay? 2 electrodes. So you see those right here, okay? And as I said, the earliest or the first vacuum tube had 2 electrodes in them. And from there, you get diode. 2 electrodes, diode. And when they came up or invented a solid state version of this vacuum tube, the naming convention was carried over. And so the first solid state electronic device was also known as a diode. Simply stated, it just means 2 electrodes, but the nomenclature comes from or is derived from the earliest vacuum tube. Okay. So the earliest vacuum tube was basically something like this. enclosed glass cylinder, which had a cathode and an anode, and it had a heater filament anode. And apologize. What they did was they applied electricity and voltage to the heater filament, heated it up at very high temperatures. The cathode, which is made out of some sort of metal, released some electrons that would float above the surface of the cathode. Okay. Right about there. And what they discovered was, since these are negatively charged particles, if you apply a positive charge at the opposite end, they would be attracted to that plate. And if you can complete the circuit, you now have movement of electrons. Okay. And what direction is the current flowing? Up or down? Both, actually. There's actually, well, in this case, we'll stick with just one convention, but there are two directions of current flow. And one is known as the Hole flow, H-O-L-E, Hole flow. The other one is known as the electron flow. So it's electron flow current or Hole flow current. But for the purposes of our classes and the education that we are undergoing, we always take the flow of current as opposite to that of the electron. So the electrons are flowing in this direction. We say current is going in this direction. And if you pay attention to the polarity and the flow of the current, you will notice, again, this is something going back to EE 113. For a power supply, current always goes from minus to plus because it is supplying energy, which holds true in this case. And the reason I'm showing this is because this is also, when we get to the diodes, the PN junction diodes, this would be the exact same circuit, except the vacuum tube would be replaced with our solid state PN junction diode. Okay. So this is the earliest example of a vacuum tube. So the vacuum tube diode. Now, what they noticed was they needed to control the flow of electrons. So they introduced a third electrode in there, and that became triode, 3 electrodes. Then inserted a fourth electrode and a fifth and a sixth and a seventh. And so you had a diode and a triode and a quadrode, pentode, hexode, and so on and so forth. I think the maximum number of electrons I ever read about was, I think, 12 or 13. Never seen one in real life, but I have read about it. I'm sure it existed somewhere in the world. But I've seen actual vacuum tubes. And they're actually making a comeback. There's now, for high definition and high fidelity audio applications, there are vacuum tube manufacturers out there. Anyway, so from vacuum tubes, we went to discrete components. Those discrete components were transistors, earliest ones. And from those, just a few years later, was the invention of the integrated circuit, IC. And now, of course, we have surface mount devices, very large integration, very, very large integration, and very, very, very large integration. Okay, so SSI stands for small scale integration, small scale integrated circuits. MSI is medium scale, and VLSI is very large scale integrated circuits. That's where the name VLSI comes from. Actually, this should be here, and then they should be here. So again, depending on the scale of integration. First, we had SSI, then MSI, and then VLSI. And now everything's in VLSI, but it's still all just called as VLSI. And this is something that you would take in your senior year, is VLSI classes. So the modern electronics era. How many have heard or seen of this picture before? Maybe not. It's become very famous, actually. As an electrical engineer, you can't escape this image. These two, I would say. Okay, this was at Bell Labs in, like, I think shortly after World War II, late 1940s. There were these three scientists or engineers who were working at Bell Labs, and they made a working prototype of a solid state transistor. So this was the first solid state device that was displayed to be working efficiently. So this is a plastic, this triangle that you see is a plastic device with a germanium point, and they were able to display how current flowing through from one point to another would be rectified and controlled by a third terminal. Okay, so this was the first solid state device, which was the bipolar transistor. And a few years later, they were awarded the Nobel Prize in Physics for this invention. Okay, I believe, let me see, Bardeen, I believe, was either the first or the second one to win 2 Nobel Prizes in 2 different fields. Or no, not 2 different fields, but 2 Nobel Prizes. There are very few recipients in the world who actually have won 2 Nobel Prizes. One of the other ones was Madame Curie, and she won it once for physics and once for chemistry, I believe. Anyway, interesting piece of history over there. Shortly after that, a few years later, there was simultaneous invention of the integrated circuit in 2 different places. Jack Kilby at Texas Instruments was working on the integrated circuit. He was actually a young engineer hired out of, I want to say, UIUC. And he was working at Texas Instruments, and they had like a problem. They were trying to create this kind of miniaturized circuit. No, sorry, not a miniaturized circuit. They were trying to create a circuit on a regular board, and it was causing problems. So he had the idea of why not take all of these separate components and put it all together onto one silicon block or one semiconductor block. And so that's what he did. He took all those components, instead of mounting them discretely on a circuit board, he took all of those components and built them directly inside one semiconductor block. And that's how the first integrated circuit was invented. Okay. And just shortly, a few months later, Bell Labs, the same engineers and scientists, they also presented their work. So there was simultaneous invention of the integrated circuit. Okay, so for a long time, there was a dispute over who actually gets credit for this. And eventually, with all the papers and the publications and, the trail, they decided that Jack Kilby should be awarded with, or credited, not awarded, credited with the invention of the integrated circuit. He was an engineer, and eventually in 1998, or in 2000, I believe, nearly 40 years later, was awarded the Nobel Prize in Physics, even though the invention is technically under like engineering. And so for a long time, the committee would not accept this invention under the classification of physics. But again, interesting piece of history over there. So integration. Why is it called an integrated circuit, right? We have PCBs with discrete components. Everyone, I'm assuming, has worked with a PCB, and then maybe over here, maybe at a different different high school project or a college project, you might have worked with an actual PCB, like designing and creating your own PCB, perhaps. Some of you may have had that experience. But what is a PCB? It's a circuit board. It's basically a connection of wires. You have components that are mounted on a board, and it's just a bunch of wires running from point A to point B, point C to point D, right? And those wires are in two-dimensional form. And so it looks as if it's printed on top, and it literally is printed based on the techniques you use. So it's basically a wire that's connecting diodes, resistors, capacitors, transistors, everything. Integrated circuit is exactly the same as a PCB. All you're doing is you're taking that integrated circuit, you're taking that PCB, the printed circuit board, and you're shrinking it down to the microscopic scale. And that's it. You're integrating all of those components, all of those wires, everything down into one small silicon chip. Hence the name integrated circuit. It's all integrated into one piece of semiconductor material. And that's also where the name microchip comes from. But we'll talk a little bit more about that later. And there's Noyce and Moore at Fairchild Semiconductor. That was a spin-off. During the early days of semiconductor invention, semiconductor industry, this was even before Silicon Valley term was coined. There was a lot of movement everywhere. So the three inventors of this transistor, they had a falling out. Okay, everybody's ego got in the way. They had a big falling out, and they all went their separate ways. And Bardeen, I believe, went on to become a professor, and Shockley stayed at Bell Labs, but they all split. And from there on, different companies were founded. So Fairchild Semiconductor was one of them. And you might have heard of Noyce and Moore. They went from Fairchild Semiconductor and they went on somewhere else. Anyone know where? They founded Intel. So Gordon Moore, Robert Noyce, and I can't think of the third founder. They went on to found Intel, Integrated Electronics, Intel. Okay, which now that was under management and started running it like a hedge fund, it went the way of Boeing, unfortunately. Like now they're waking up to realize the worth of engineers. Anyway, if you may be aware, Robert Noyce, he passed away a few years ago. He had no connection to Cal Poly, but his estate and his widow, they made a bequest to Cal Poly, where they wanted to invest and start a new school, which falls under the umbrella of the College of Engineering. And it's named after Robert Noyce. It's called the Noyce School of Computing, and primarily consists of 4 departments: computer science, software engineering, computer engineering, and EE, electrical engineering. So we fall under the umbrella of the Noyce School of Computing. Okay, and this has has provided many avenues for faculty and students to collaborate and perform research work. So keep an eye out, because there are lots of funds being awarded every year for research projects. So faculty would be or may be in need of students who want to do some research. So keep an eye out on the weekly newsletters and stay in touch with your faculty. I'm not doing any research anymore, but there are other tenure tech professors who are. And so 3 of the E projects were funded last year, and I believe another 3 or 5 may be funded again this year. So every year they have some new funding coming in. Okay, IC density growth. Moore, one of the founders of Intel, early on realized that the progress that they were making, in integrating these circuits and making them smaller and smaller, or actually increasing the sizes, he noticed a relationship between the amount or the quantity of devices they could fit in the same area every 2 years. Okay, and so he predicted that the number of transistors that they could fit in a microchip of the same size would double every 24 months. And that came to be known as Moore's law. Okay. It's more of a prediction, if you will, because a law is, by its very definition, should be inviolable, right? So it's kind of like a prediction more than a law. But anyway, more commonly known as Moore's law, and it has held up true all the way to modern times. Okay. And so this chart here shows you how the feature sizes and the complexity have both decreased and increased as the decades have gone by. Okay, so I'll explain what it means. 1970s, here you can see approximately 10 raised to 3, 10, excuse me, 10,000 devices in a single microchip, excuse me. Then almost a linear relationship as we go along. Okay, so the size, not the size, sorry, the number of transistors, the quantity has been doubling every 24 months. Okay, on the left here is the feature size. Feature size is basically the size of the actual device. And typically when we talk about microchips, feature size is basically the smallest dimension in your entire circuit. Okay, so your entire circuit could be, let's say, a unit of 100. But if there's one tiny feature in there that is about 10, then you would say your device is a feature size of 10. Okay, so feature size has been decreasing as the years go by. And that is what is allowing us to squeeze in more and more numbers of the same transistors on the same size, right? If something occupies 10 units of space, and now you squeeze this, you reduce the size in half, now you can put 2 of those in the same space. And that's what it was. With advances in technology, the feature sizes kept shrinking, and so they were able to fit in more and more and more transistors in the same area chip. And it's actually incredible how far along we have come. And I'll prove it with a point. You might be familiar with some of these unit prefixes. Right? As engineers, we work with a wide range of values, from very, 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 very large to very, 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 very small. Right? You might be familiar with some of the ones here in the middle, but I expect you to memorize this entire table. Not really. Even I don't have it memorized. So we are familiar with the ones in the middle, right? So let's talk about, since we're talking about microchips, let's talk about why and how the name came about. So when they first started building these devices in an integrated circuit, they were working with feature sizes. They were less than 1/6 of the size of a meter. So you're all familiar with the centimeter, right? Centimeter is something that you can easily visualize. You divide centimeters into 10 parts, you get 1 millimeter. 1 millimeter is also something you can easily visualize. You take half of a millimeter, you get what is your typical mechanical pencil, 0.5 millimeters, right? But 1 millimeter, and you divide that 1 millimeter into 1,000 parts, gives you 1 micron, 1 micro. So it's 10 raised to minus 6 meters. Okay, 10 raised to minus 6 meters. It's noted by the Greek letter mu, called micro. And that's where the name comes from. Microchip, microfabrication, micro technologies, microsystems. That's where it comes from. If you take 1 micron, so 1 micro is also known as micron. Hence the name of that company, Micron Technologies. Okay, so 1 micron is 10 raised to minus 6 meters. If you divide that micron into a further 1,000 parts, that is 1 nanometer. And nowadays in layman term, they throw about this, as if it's nothing. It's like nanotechnology, nano this, nano that. But it is incredibly small. On the other hand, here we have kilo, mega, giga, tera, peta, exabytes of storage that we have talked about. I'm sorry, that that you hear about. So on the small size, on the right-hand side, to give you an idea of how small a micro is, a human hair is about the size of 50 to 75 microns. Okay, 50 to 75 microns. Very, very thin. On the left, where you have thousands, millions, billions, some of you may know the answer to this. When we talk about 1 mega, it's 1 million. How much do you think is 1 million seconds in terms of time? Hours, days, weeks, months? 30 days is a good guess. No, not 10 years. 1 million seconds is about 11 to 12 days. How much do you think is a billion seconds? Any wild guesses? 110 years? It is indeed 31 years. That was a good guess. That's the difference between a millionaire and a billionaire. Okay, literally, it's a huge amount of money. The federal deficit right now is $30 trillion. 30 trillion. So 1 trillion seconds, 31,000 years. And the federal deficit is 30 trillion. If you pay off $1 every second, I'll stop over there. Anyway, the point being, as engineers, we will work with a wide range of values. As students, when you write your answers, you can write in any form you want. You can write it as, let's say if it's 1 millivolt, you can write it as 1 into 10 raised to minus 3 volts, or you could write it as 0.001 volt, right? Your answer is correct. But no matter what your value is, your unit prefix should match up, meaning it's 0.001, that is correct. 1 into 10 raised to minus 3 is also correct. If you don't use that and you want to use a unit prefix, then milli should be in there. Otherwise, your value is incorrect, right? So I do give partial credit, meaning instead of 1 millivolt, you just wrote down 1 volt. I will give you partial credit. Okay, there won't be that huge of a deduction, maybe like half a point or so. Units should always be there. 1 volt is not the same as 1 amp. Okay, so that is part of communication. If as a working professional engineer, you hand your work to a peer or to your manager, they're looking at it, and if they see it's just 1 or it's 1 amp, some value with some wrong, incorrect units, that's completely incorrect, right? And so that's something that you should practice while you're still a student. So make sure you're up to date on the unit prefixes. Okay, signal types. Before I begin, let's take a pause. Let me know if you have any questions about anything so far.
Was the vacuum tube just used to generate a current? Or what did you amplify?
So the question being asked is, were vacuum tubes used just to generate current voltage, or were they actually used to amplify? The answer is yes. Not just amplify. All electronic devices, whether they are vacuum tubes or solid state, we are going to manipulate voltage and current unlike a linear device. Okay, when we say manipulate, it could be exactly as saying one of the things could be amplification, something else could be mixing, or could be attenuation, right? Yes. That would be correct. So the question being asked is, if the heater was more hot, if the temperature is high enough, would there be more free carriers, more electrons generated from the cathode? Up to a certain limit of physics, I would have to say yes. Yep. All right. Any other questions? Okay. So two different signal types, analog and digital. By the way, when we say signal, it is interchangeable with function, waveform, and that could also be indicating either voltage or current. Sometimes you might simply say we're applying a signal of 12 volts. There's a signal of 12 volts, meaning it's a voltage of 12 volts that's being applied, or an amplitude of 12 volts. Okay, so signal is the same as function. Hence, also we use signal generators or function generators. In the labs, we use function generators. We can also say waveforms because it's the shape or the form when it's plotted with respect to time. So analog signals basically have continuous values, whether they are voltage, current, power, doesn't matter. Any quantity has a relationship with time. And when you plot the value of the waveform with respect to time, 0 moving in the positive direction, you would see the shape of that waveform, okay, shape of that signal, hence waveform. It has continuous values. In other words, it also has infinite values because you could pick any moment in time and it would have a different value. Okay, any moment in time would have a different value. The sound that I'm making right now is being captured by the microphone. That microphone is converting it into electrical signals, right? So if I observe the sound of my voice or the waveform in an oscilloscope, it would be a random signal that looks like this, right? Has a different value. Depending, frequency can change, volume, amplitude can change. If I speak loudly, if I yell, then the amplitude would be higher. If I speak very, very softly, it would be different. If I speak in a very high tone, frequency is going to be very high. If I speak very low, that's going to be a different frequency, right? So those are all analog signals. Then we have digital signals. Now, digital signals basically derive from analog, and typically we work with only two levels in digital signals, either 0 or 1. Okay, zeros or ones. So it's either low or high. And I'm assuming you have taken 133 logic design, where you learned about digital signals, and you've done the is it 329, or is it yet to come? 329 is yet to come. Okay. All right. So it's we have two different logic levels, and we use the binary number system for logic design: logic 0, logic 1, low and high. Analog or a analogy can be made with a light switch. Light switch off, that's logic 0. Light switch on, that's logic high. Now, there are many different kinds of digital systems. The voltage levels could be very different depending on what the system that is being used. Initially, or typically, it was just 0 to 5 volts. 0 to 5 volts. So 0 would be low and 5 would be high. Okay. But when you're talking about miniaturized circuits, that generates a lot of heat. Okay, so we want to keep the power consumption low so that the heat thermal dissipation is low. And so then we move from 0 to 3.3 volts is acceptable. Okay, and so most modern devices would run on 3.3 volts. These are known or said to have discrete values. Okay, discrete values, because at any given point in time, that value could be fixed. So if you take a range, the value of the signal is fixed at a particular level. But when you get to a different time point, that level could be different. So there's two different values, so discrete values. So you might have taken a class on continuous time signals, or you probably will take a class on continuous time signals and discrete time signals. Okay, so two different classes. And the high levels and the low levels have certain tolerance built into it. Meaning, if the signal is between a certain level or above a certain level, you'd call it logic high. And if it's below a certain level, meaning right here, so if this is 0, anything below this is known to be high. Sorry, known to be low, and this would be high. So there's a certain tolerance level that's built into the system. Okay, in between is not allowed, so it's null. The system wouldn't know what to do. But typically, that's not usually a problem, right? Circuit designers make sure that the voltage levels would be either high or low, depending on the application. Yes. Yeah, so the question being asked is, why is this all the way here, low, right? So it's basically, let's say if it's 0 to 5. So let's explain with an illustration. If this is 5, for example, and there are always fluctuations in circuit, right? So if the 5 dips below, let's say it might go to like 4.9, 4.8, let's say, and let me just mark here 4.8. Well, we want it to be high, so we built tolerance into the system so that 4.8 is also considered as high. So there is a range of voltages where the system would accept it as being logic high. And so this would be considered as high. And conversely, when it's logic low, sometimes there's noise in the circuit. And so instead of being completely 0, you might have like 0.1, 0.2, or even 0.3 volts. But you still want it to be considered as logic low. And so you would say the range between 0 and 0.3 is logic low. Okay. All right. Any other questions? That's analog and digital. Then analog, as I stated, has continuous values. Digital has discrete values. So if you want to recreate a digital version of an analog signal, you would sample the analog waveform at certain points in time. That is known as the sampling rate, right? The sampling rate. And so the more samples you have, the more accurately you can replicate that analog signal. So when we talk about video transmission, we still have over the air, OTA, like you can use antenna and get free TV. Okay, you can get like, if you have a really powerful antenna, you can pull in signals from like 50, 60 miles away. Television stations are broadcasting all around us. And you can pull in this video signal over the air, right? Now, in the age of the internet, we have streaming services. So streaming services, you're constricted by the bandwidth. You have wires that are carrying the signals, right, over the internet. And so sampling rate, bit rate, the resolution, and then the compression all factor into the quality of the signal that you're sending out. Simplest example is right here on the board. The analog signal on the left has been sampled, let's say, between here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 samples within that first range. Okay. If I send these 9 signals, I may need only a limited amount of bandwidth or limited amount of space to send it. If I double the time interval, if I half the time interval, then I have to double the number of samples. So instead of 9, I have 18 samples. I'd have 18 samples, but I would need more space to send those 18 samples. But my reproduction at the receiving end would be much better, right? And so it's always a fine line or a compromise between how many samples you want to take for a digital system, depending, again, on our application. If you are just sending it through a wire locally, that's fine, almost unlimited, right? If you're sending it over the internet, then we are limited or constricted by the bandwidth. So digital signals and analog signals have different considerations, and that is something that you will learn as you will go along. Okay. All right. So we are out of time. We are at 12. We'll end class here today, and I will see you all on Friday. I haven't decided on the quiz yet, but it'll be something very short, something about circuit analysis for Friday. And then also, don't worry about the due dates on the assignments. I need to, sit down either Thursday or over the weekend and just fix through everything. Okay. So there's nothing due as of now, but I'll make certain that I post an announcement. So in your Canvas pages, make sure you check the box that says, send me, when a notification arrives on Canvas, like when an announcement is posted on Canvas, send me a notification.